So good morning, everyone. Welcome back to our part 2, talking about conservative vector fields, and today the fundamental theorem of line integrals. When we were last together, we broke off midway through example number 2, and for the sake of time, I just finished that after class and appended it to the video. So if you didn't get a chance to watch that, make sure you go and watch the last 10 or so minutes of that film. I'd like to just dive straight into the lesson. So we are again in 17.3 on conservative vector fields, and we are going to begin exploring their connection to line integrals. And good news, it's a nice, simple connection. So in general, when calculating a line integral, we must begin by parametrizing the path, because different paths lead to different amounts of work to focus, or different amounts of work to focus on one particular application. Not so if the field is conservative. And remember, when we say conservative, what we're saying is that f is equal to some gradient field. So it's equal to the gradient of some potential function phi. So the fundamental theorem for line integrals. So let R be a region in R2 or R3, and let phi be a differentiable potential function defined on R. If big F is equal to the gradient of phi, that is, F is conservative, then the work, which we always find by finding the line integral of F, the tangential component of the force along the curve, or just F dot dr, can be calculated by simply looking at the difference in the potential function.
I think you have a question.
Potential function at B minus potential function at A. Question?
Yes, I saw you put the homework 17.3 due in June 10. Is that wrong, Nay?
That seems a little bit late. Let me make a note and check on that. Thanks, Twee. I appreciate that.
Thank you so much.
Thanks for that note, Twee. So here's the meaning of the fundamental theorem of line integrals. If big F is a conservative vector field, then the value of a line integral big F depends only on the end points of the path. For this reason, we say that the line integral is independent of path, which means that to evaluate line integrals of conservative vector fields, we do not need to parameterize the path. You all just finished your homework on 17.2, and that very first step in all those questions is a parameterization. Even sometimes it's given, but here, if you happen to be working through a conservative vector field, we do not need to parameterize the path. This is good news. And let's maybe see why this would be the case. So if you have a closed path, and that would mean you start at A, and then you run all the way around, and your A is also your B, they're the same point, then we would say that the work would, and it's through a conservative field, the work would be the potential function at the final point, B minus the final point A, or the initial point A, but notice that our B is actually the same as our A, and so the total work done would be 0. So this would give me the work around a closed path, and then in general, if we just had A and B, what we're saying is that the work required to go along path C1 is equivalent to the work to go along path C2 is equivalent to going along path C3. Like, it doesn't matter what path you take, as long as you have the same initial point and same end point, you're going to get the same work. So here you have path independence. And In the other case, you have showing that the work to go around the closed path of f dot dr, if it's a conservative field, will be 0. Questions about any of this? I can't help you on that one, Enrique. There's a chem question in the chat for those of you that are chemists. But I do know in looking at my applications, I haven't seen any connections to chemistry. Lots of connections to electricity and magnetism, but not stuff that I've seen in chemistry. Very good. All right. So I'm not going to prove this particular theorem. The proof's in the book, but I did want to point out one part of the proof, namely that the proof makes use of the multivariate chain rule. I don't know if you remember learning the multivariate chain rule in Calc 3, but you would have started with phi, and you'd said phi is a function of x and y and z, and x is a function of t, y is a function of t, and z is a function of t, and you would have drawn these little diagrams, and that would have told you how to write the general form for the multivariate derivative of phi with respect to t. And what was interesting when you learned that, it was probably a little bit intense and overwhelming, and probably in the back of your mind you're thinking, oh my gosh, this is the chain rule, and I know I use the chain rule a whole bunch, and this is also intimidating. And then it never came up, like ever again, except for on maybe a final exam or a test. So you might have wondered, what was the big deal there? And so the reason why we needed that multivariate chain rule is it's going to show up in this derivation, and then also I believe in a later derivation in this chapter. So once again, making the point that in this chapter, we're going to pull a whole bunch of the concepts we've learned from across calculus all together into a single topic. So it's pretty cool stuff. So I'd like to look at example 1 again and kind of revisit what we came up with. So let me switch over to the camera and work through it. Okay, so we previously, yesterday, showed that if we had this field big F equal to 3y plus 4, comma 3x plus 5, we showed that this field was conservative. That is, we showed that big F was equal to the gradient of phi. And then we found that phi was equal to, I believe, 3xy plus 4x plus 5y. So we showed that yesterday. Well, thanks for answering the question, Joseph. This isn't like Hess's law. Hess's law has to do with the sum of enthalpy and how that changes over reaction. So back in our class, so we want to find the work to travel through this field around the unit circle. And so we want to go across this path. But good news, since our field is conservative, all we care about are the endpoints. So notice the work, which is the line integral across C of f dot dr, is going to be the work across C of a gradient dot dr. And if we were approaching this question like we've done in the past, our first step would be to parameterize the unit circle. But here, because we have a gradient field, we can simply evaluate the gradient at the endpoint minus, not the gradient, the potential function at the endpoint minus the potential function at the initial point. So this will be gradient at minus 1, 0 minus the gradient at 1, 0. And so we have y being 0 in both cases. So those These terms are going to be 0. So we'll have -4 minus 4, which is pretty close to -8. I'm not sure how I got -9 in my notes online, but you get a work of -8. So this -8 represents the work to go from 1, 0 to -1, 0. Questions about that?
Is this kind of how it's related to like gravity being a conservative force, so we only care about the change in height and not its specific position change?
It's definitely related to that. So gravity would be an example of a specific application of this. And we're actually going to go there. We're not going to talk about gravity, but we're going to talk about conservation of energy in just a couple minutes. So good call. Other questions? Very good. All right. So notice that the only challenge in answering this question is that you have to know what that potential function is. And so we actually did all the hard work yesterday when we were finding those potential functions. The example 2 revisited is just like the one we just did, just picks up on the question from the end of class yesterday. Same thing, find your potential function, calculate the work, and we recognize that our force field is a gradient field, e.g. it's conservative, and so we can simply evaluate the potential function at the 2 endpoints and find the difference. So I'm not going to work through that, same deal as before. We already talked about this a little bit, but there's this question of what is the work to travel around a closed path through a conservative field. And in a closed path, you end in the same place that you start. And so you're going to have your phi at B minus your phi at A, but the B point is the same as the A point, so the work will be 0. And so we get this little theorem that says that if you're working over a nice region and your field is conservative, then the work to go around a closed path will be 0. There's a variety, if you go through your text, there are a variety of related claims and theorems that can all be made by adjusting hypotheses. And a lot of the hypotheses that are going to change are these ones around what kind of region. So if we change the type of region, then we sort of change the type of theorem. But I've really focused on the theorems that I think will be the most helpful to you in this class. Okay, so here's a summary of what we've done so far. So we've established 3 equivalent properties of conservative vector fields, F defined on an open connected region. So the first thing is that there exists a potential function. That means it's equal to a gradient field. The second is the fundamental theorem of line integrals, that the work required is just the difference of the potentials from the end minus the potential at the beginning, which gives us path independence. And the third equivalent statement would be that the work to go around a closed path would be 0 on all closed curves. Or if you like, path independence is the same thing as the field being conservative, is the same thing as the work going around the closed path being 0. The last thing I want to do is look at an application of this to physics. So for those of you that have studied physics, you're probably wondering what's the connection between conservative and potential that we're talking about in calculus and conservative forces and potential energy as outlined in physics. And so let's just start to work through this derivation. And it's a little bit long. For those of you that are printing out the notes, you'll notice that I gave you 2 full pages to work through this derivation. Can you see my notes?
Yep.
Okay, thank you. All right. So we're going to start by assuming that F is not conservative. So if F is not conservative, then the very first step in any sort of work integration is to parameterize. So this tells us that our work will be equal to the line integral. But now we're going to go, now it's no longer line integral, now it's going to be a definite integral from a to b of f. So you've got to take that field and you got to substitute in your parameterization, so r of t. And then we've got to replace the dr with r prime of t dt. All right. Now, you may remember, well, if you've had physics, you better remember, because it's like day 1 stuff, that we have this formula for F in physics. What's the formula from Newton's second law for F? F equals ma, mass times acceleration. And what's the relationship between acceleration and the space curve? Make sense? So now I want to relate. So I'm looking for a different color pen. I want to relate
acceleration.
Yeah, a
Second
and
derivative.
Which derivative?
Of position, whatever your position is. A second derivative is acceleration.
Second derivative, exactly. So this would be r double prime of t. Okay. So our work will be equal to the integral from a to b of f. F is going to be mass times acceleration. So this will be, here's the mass. The acceleration is going to be our r double prime of t dotted with, notice this is a dot, this is just a multiply, dotted with r prime of t dt. We have mass times acceleration. This is our force. Here's our differential element. Questions so far? Very good. So let's do a little bit of scratch for a second. So if I have ddt of r prime of t dotted with r prime of t, I get to use the product rule, and so I would get r double prime of t dotted with r prime of t plus r prime of t dotted with r double prime of t. So notice you got double primes and primes, prime and double prime, but with the dot product doesn't carry the order. So this would be equal to 2 r double prime of t dotted with r prime of t. Questions about this scratch work?
Yep. Would it make sense just to square the R prime of t up there?
This is a I think this is not a squaring. I mean,
because
maybe you could.
It's a dot product. It's not multiplication.
Yeah, it's a dot product. So I think that it would look like you get the same result by using the chain rule, but I feel like that would develop, it wouldn't hurt you in this case, but it would develop a bad habit that might hurt you in some other situation. So good question, Titus.
I agree.
All right. So going back to what we had before, so we have this, we have R double prime dotted with R prime, and here you have 2R prime dotted with R, 2R double prime dotted with R prime. And so we're going to replace this bit here with 1/2 times the derivative, ddt, of R prime dotted with R prime. Questions about this?
Where we get a half from?
The half is coming, trying to counteract the 2 that was out front in our scratch work.
Got it.
Yeah, good question. Very good. So let's continue to keep going. So we have that the work is equal to 1/2 the integral from a to b, and I guess I can pull the m out front as well. And we have a ddt of R prime of t dotted with R prime of t dt. Vector dotted with itself can be written as the square of the magnitude. So this would be ddt of R prime of t magnitude squared dt. Now, here's something kind of cool. Notice that we have an integral here with respect to dt, and then I'm taking the integral of a derivative. So what happens if you integrate a derivative?
You get back to your argument.
Yeah, they undo each other, exactly. So this will be m over 2, and then our argument is going to be R prime of t, quantity squared, evaluated from t equals a to t equals b. We still had to account for the fact that it was a definite integral. So this would be m over 2 times magnitude of R prime of b minus squared minus magnitude of R prime of a squared. Cool, cool. And then we have a whole bunch of R primes. What's another name for R prime? Like, what does R prime give us in terms as an application?
It's our velocity.
Yeah, this is our velocity. So this would be m over 2 times the velocity at b squared minus the velocity at A squared. So notice, let me say that again. So this would be 1/2 mv squared. And what's 1/2 mv squared equal to?
Kinetic energy.
That's the kinetic energy. For those of you that haven't had physics, you just get to smile and nod, and be like, oh, that's so cool. My friends that have had physics must be really enjoying themselves right now. And so all this stuff, this work, would be equal to the kinetic energy at B minus the kinetic energy at A. Questions so far?
You could get rid of the absolute values because it was squared, so it didn't really matter. Just clarify.
Correct. I think correct.
Okay, cool.
Because it became a. But I think those absolute values are actually there. I think that's my bad, not. Yeah, I think because these are still vector quantities. Thank you for that question. Okay, let's do a little bit of background stuff before we dive into the second part of the question. So we want to talk now about potential energy. So suppose that big F is now a conservative field. Before we didn't assume conservative. So if big F is conservative, that means it's a gradient field for some potential function phi. In physics, we define the potential energy to be negative the potential function that we have in calculus. So this one right here is potential energy. This one right here is the potential function. And the question is why? Why would they be opposite signs?
Because if you move it to the other side, it equals 0.
0. I think for me, when I think about this intuitively, what I think is that potential energy, you have more potential energy when you're up high, and so because then you can go down, and so in a sense, the potential energy is always pointing down, because that's the direction you're going to get it. Whereas our gradient is always pointing uphill. That's kind of my intuitive explanation for why this is the case. For the sake of time, let me work through the last bit on my pre-done notes. So the work, now we're in a conservative field, would be F dot dr. F would be a gradient field. And so we can replace that gradient of the potential function with the potential energy, and we picked up that negative for the reasons we just talked about. Since it's conservative, we can use our fundamental theorem of line integrals. And so we just look at the difference in the two potential energies. So potential energy at the end minus the potential energy at the beginning, and then this negative is still hanging around out front, which causes the whole thing to turn into potential energy at A minus potential energy at B would be the total work done.
10:30, Dusty.
Cool, and almost there. So thank you, Robert. So the conclusion is that we found that the work is the kinetic energy at B minus the kinetic energy at A. We also found that it's the potential energy at A minus the potential energy at B. And we can move all of our P's and we can move all of our P's or our A's and B's to the same side. And so notice the potential energy at A plus the kinetic energy at A is equal to the potential energy at B plus the kinetic energy at B. which is to say that the total energy, potential plus kinetic, is conserved. It doesn't change, which is pretty cool. Questions about this? Very good. Last thing is just a note that there's a flow chart on the back of the notes that helps to organize some of the information that's happening in the section. And so we'll talk about this more probably at the end of section 17.4 on Green's theorem, but I wanted to direct it to you for those of you that like flow charts more than you like bullet lists. So, oh, nice, Titus. You've all realized your full potential, just like in a Disney film. So you've all realized your full potential. May you all go out and conquer the world. Thanks everyone today for the short class today. I look forward to seeing you all tomorrow to start talking about Green's theorem. Take care, everyone.